Hi guys, welcome back to our quick review. This one is going to cover Chapter 1, the intro to physical geography. And we've already had this lecture in class, so I'm going to go over this quite quickly and hopefully not too quickly. If you have any questions, of course, you can post those in the chat section on the Canvas course, and we'll go from there. All right, so Chapter 1. So basically, we divide geography into two main sections. One we call human geography and the other one we call physical geography. This course, of course, is physical geography. Now, human geography will cover like world politics, economics, culture, language, religion, etc., and both where those are distributed over the planet and how that came to be, and how they are all interrelated. On the other hand, physical geography is going to cover these four geographic spheres. So the field of physical geography is broken down into the study of the atmosphere, that's the gaseous layer that surrounds the Earth, the hydrosphere, all the water on the planet, the biosphere, all the life forms, and finally the lithosphere, which for now we'll talk about like the rocks and the soil and the sediment, but we'll learn later on that it has a more specific definition. So the atmosphere, again, that gaseous envelope that's surrounding the Earth, not very thick, to tell you the truth. We'd say probably about 60 miles. Beyond that, the molecules are so few and far between, we really don't consider it to be atmosphere anymore. And you'd be studying astronomy rather than be studying geography in that case. About half of our atmosphere is actually found in the lower 4 miles. So you can see how important it is that we look after this atmosphere. The hydrosphere, that's the oceans and the seas and the lakes and the glaciers and the rivers. So all kinds of forms of water, even the water in the atmosphere. We'll be looking at this in a later chapter and looking at the interconnections between the hydrosphere, the atmosphere, the lithosphere, etc., and the biosphere. Speaking of the biosphere, that's the life forms. Mainly plants and animals is what we'll be discussing because we can more easily map those out. We can see animals, we can see plants, we can see where they naturally would occur, and that will be our focus. We're not going to focus on fungi and algae and things of that nature, or even single-celled organisms. So the lithosphere. We can see back here we have rocks, we have rotten rocks over here that the plants are growing on, that would be a soil. Pieces of rock which broke away from higher elevation and worked their way down through streams to be deposited in low spots, we call those sediments. And even volcanic ash, if that landed, we'd be looking at that stuff too. So back in, or looking forward to chapters 7, 8, 9, we'll be looking at that. We're going to start by taking a quick look at the age of the Earth. Our planet has been around for about 4.6 billion years, so you want to remember that number, 4.6 billion years. It's broken down geologically into eras, periods, epochs, and basically we can look at the geologic record and see there wasn't very much life for the first few hundred millions of years, and about 3.5 billion years ago we started to pick up some single-celled organisms like blue-green algae and cyanobacteria. Those would slowly start to change our atmosphere. In the rock record about 590 million years ago, we see a change from single-celled organisms to multi-celled organisms, and an explosion of life. These are what we refer to as the old life forms, or the Paleozoic era. By about 245 million years ago, 90% of those species that were around went extinct, and of those that were left, they speciated into new plants and animals, etc., into middle life forms, which we refer to as the Mesozoic era. That's composed of the Triassic, Jurassic, and Cretaceous. And from that, you can see, yes, that's the age of the dinosaurs in this era. That came to a crashing end at about 65 million years ago, and about 75% of all species went extinct. The remaining 25 dominated by things like mammals. So the Cenozoic, the new life forms, that is the age of the mammals. Again, those eras can be broken down into periods and epochs, etc. We are not going to take any time to explore that right now. That will be for a later chapter. But basically, what I do want you to know, age of the Earth, about 4.6 billion years. Now in class, we also discussed the order of the planets, and at the top up here, we see the letters for Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. No Pluto anymore. As you can see, that most of the other planets are all in the same plane, or the same plane of ecliptic, so they all go around the sun in pretty much the same layer, the same level, the same plane, whereas Pluto was elevated. I think the orbit was elevated something like 17 degrees or so. It didn't fit the rest of the planets. Also, we tend to have the rocky planets towards the interior orbits around the sun, whereas the outer planets are more gaseous. They're more like Jupiter. We sometimes call those the Jovian planets. So it didn't fit the model Pluto out. So I really want you to know Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Those are our planets. If we did include Pluto, we'd have to include a lot more things in there in space going around the sun that are very Pluto-like. So we just threw Pluto out. Now, we are going to focus this entire course on the Earth, which is the third rocky planet from the sun, the third rock from the sun. Its average distance is about 93 million miles. We can see in this slide here that here's that plane right here, the plane that those planets take around the sun, and there's Mercury, there's Venus, and finally Earth. Earth, the third planet from the sun. Now, this is certainly not to scale. We are 93 million miles away. We would be about the size of in this scale, if the Earth was that size, the sun would probably be across the street from the college. It's that far away. Now, again, I'm just highlighting here that path that those planets take around the sun, this path right here, that's called the plane of the ecliptic. That's going to be very important in just a little while. Now, here's the Earth going around the sun. That average distance, again, 93 million miles. And the Earth has its own moon orbiting the Earth, about 238,000 miles away. It takes 29 and a half days for the moon to go around the Earth. So we get a full moon every 29 and a half days, and that's when the moon is on the opposite side of the Earth from the sun. So sun, Earth, the moon is over here. We would get a full moon because the reflection of the moon would shine back to us and we'd see a full moon. And then half of 29 and a half days, so let's say about 15 days later, we would have the moon over here, and the moon would be up. During the daytime, we wouldn't see the moon, and at nighttime, we wouldn't see a moon, and basically, nighttime, as the Earth spin here, we wouldn't see the moon. We call that a new moon. So a new moon, you can't see the moon. A full moon, you can see the whole thing. Let me show you a little bit of a diagram of that right here. So with the sun's rays coming in, imagine this is the Earth, this is the moon going around the Earth. It takes, to get from this position here to this position here, that would take about 15 days. And to complete the cycle, to come all the way back around, would take a total of 29 and a half days from when you started. So within that 29 and a half days cycle, we would go through a new moon cycle to a full moon and back to a new moon. Now, the impact of that is widespread, but basically, when we have the Earth, moon, and sun all aligned up, be it a new moon or a full moon, the gravitational pull means that we're going to get very large tides on the coastlines. Conversely, when we have a quarter moon, be it the first or the third quarter, when the Earth, sun, and moon are operating at a 90-degree angle, then we get the least amount of we would not get the largest tides. We would get mild tides. So mild tides are referred to as neap tides, whereas the very, very strong tides are referred to as spring tides. There's nothing on your upcoming exam about that because I'm leaving the discussion of the moon for later, but also leaving it for the course in astronomy. So you can take a class in astronomy of our solar system, and they will go into in depth about the moon. Okay, so our planet, the Earth, third rock from the sun, how big is it? Well, if we round off to the nearest 1,000 miles, we can measure the Earth in terms of the radius that's going from one edge of the Earth into the center of the Earth. That would be the measure of radius, and that's 4,000 miles. If we go from the edge of the Earth and come all the way out the other side, going straight through the middle. That distance there would be the diameter, and that would be 8,000 miles, so double the radius. And if we want to go all the way around, so keeping on the surface, going all the way around and coming back to the other side, that's 25,000 miles to circumnavigate the Earth along one of the fat parts. So radius 4,000 miles, diameter is 8,000 miles, circumference is 25,000 miles. I need you to know those. These are measurements rounded off to the nearest 1,000 miles. Now, in reality, it would look like we're living on a sphere, but in order to be a sphere, we would have to measure the diameter in multiple places and have it always be the same. So we'd have to measure the diameter across the equator from pole to pole, from mid-latitude to mid-latitude, and all those numbers would have to come out to the same number. Basically, if we did this to the nearest 1,000 miles, that would be true. But if we do it with a little bit more accuracy, say to the nearest 1 mile, we can clearly see that the distance from, the diameter across the equator, we refer to that as equatorial diameter, is 7,927 miles. If we measure from the North Pole straight down to the South Pole, that distance is only 7,900 miles, a difference of 27 miles. So the Earth is 27 miles fatter along its midsection over here. Well, that's to be expected, right? The Earth is about 4.6 billion years old. It's got about 5 billion years left to go before the sun gobbles it up. The sun will ultimately run out of fuel. It will implode, then move outwards, gobble us up. But that's 5 billion years from now. Don't worry. What the point I'm trying to make is that if the Earth is looked at like an organism, we can say that organism is basically halfway through its life cycle, and it's going to get a little bit of bulging going on around its midsection, just to be expected. That's not what's really going on here. What is going on is that the Earth is spinning. It's always spinning from west to east. So imagine this spinning around and around and around and around. And basically the inside of the Earth is not locked down as solid. We still have some non-solid layers in there. And due to centrifugal forces, we're going to have an outward motion where it spins the fastest. Well, imagine the Earth is spinning here, but it's not going anywhere in a day. It's just going around and around. But if you're at the equator, you're spinning around 25,000 miles in a day. That's 1,000 miles per hour. And that's going to have a force that exerts outwards towards where we get that greatest speed, or the greatest angular speed around the equator here. So the Earth is bulging out. It's bulging out 27 miles. That is due to the fact that we are spinning, and we refer to this bulging out at the equator as, let me get this rid of here, equatorial bulge. So equatorial bulge is a name for that 27 miles of bulging at the equator. So we are not a perfect sphere. We're almost a perfect sphere, about 0.3% away from being a perfect sphere, but we can't call ourselves a perfect sphere. We have to say we are sphere-like. And in science, we can use the letters OID at the end of another word to say that this is almost something, or very much like something. So instead of being a sphere, we are a spheroid. What kind of spheroid? We're one that's kind of thinner on our north-south axis, fatter in our east-west axis, so we're kind of squashed. So the official name is an oblate spheroid. That is the official name for the shape of our planet. We live on an oblate spheroid. Now this oblate spheroid, I said, has an average distance between us and the sun of 93 million miles, but that is not always the case. Sometimes we are closer to the sun, and sometimes we are further from the sun. So the closest we would ever get is about 91.5 million miles, and the furthest we would get is about 94.5 million miles. That's because we don't have a perfectly circular orbit. We have an elliptical orbit going around the sun. It's about 3 or 4% away from being perfect, but that is enough to account for this 94.5 million miles, the furthest distance, and 91.5 million miles, the closest distance to the sun, with an average of 93 million miles. Now, what you don't immediately see on this diagram, but it should jump out pretty quickly. 94.5 million miles, when we're furthest from the sun, occurs on July 4th. Now for Southern California, that's a pretty hot season. It's the start of summer, about 2 weeks after the start of summer. Conversely, January the 3rd shows that we are 91.5 million miles away from the sun. That is our closest point. And by the way, the closest point is referred to as perihelion, and the furthest point is referred to as aphelion. So aphelion, 94.5 million miles away from the sun, July 4th is when that occurs. Whereas perihelion, 91.5 million miles away, occurs around January the 3rd. Now you might think, hey, this teacher's lost his mind at this point, but the reality is the distance between the Earth and the sun must not explain why we have seasons. It must not explain why we have hot weather in LA on July 4th, but we have pretty cold weather by comparison in January. So something else must be going on, and indeed that is true. So let's get into the real reasons why we have seasons. Before we do that, just take a quick look at this. So on perihelion, January 3rd, the sun would appear in the sky a little bit larger than it would in July, and the reason for that is that in July we are further from the sun than we are in January. Again, that difference is not enough to explain why we have different seasons. It would explain a little bit about why the southern hemisphere might get more incoming solar radiation during their summer months than the northern hemisphere would during our summer months. So again, remember this line? That is the plane of the ecliptic, the path that the planets take around the sun, including the Earth. Now, mathematicians, you might recognize a line here that intersects that plane at a 90-degree angle. So the relationship between these lines would be this one, this red line here, is perpendicular to this yellow line. And if this yellow line is called the plane of the ecliptic, then this red line is referred to as, and its real name is, the perpendicular to the plane of the ecliptic. Again, the perpendicular to the plane of the ecliptic. I'm going to run out of words. My throat will get too sore if I keep saying that. So scientists often will just abbreviate or cut things short. We would just refer to this line as the perpendicular. But perpendicular to what? Well, it is perpendicular to the plane of the ecliptic. So when we talk about the perpendicular, this is a line that we're referring to. And here's that line right here. This line running straight up and down is the perpendicular. That's the same line that we just looked at. Our Earth happens to be tilted at an angle of 23.5 degrees. So our North Pole is not straight up and our South Pole straight down. They're actually tilted 23.5 degrees from the perpendicular to the plane of the ecliptic, or abbreviated, we are tilted 23.5 degrees from the perpendicular. And that means the North Pole is tilted by that same amount. So the North Pole is tilted 23.5 degrees from the perpendicular, and the North Pole is always going to point in the same portion of space. That's important because as we go around the sun, that will mean at certain times of the year, the sun is going to be over here on this side, and other times of the year, the sun is going to be over on this side. So the rays of the sun are going to hit different portions of the Earth at a 90-degree angle. It's going to light up and it's going to warm up different portions of the planet at different times of the year. So axial tilt, critical to why we have seasons. As you can see here, now we have to keep in mind, this diagram here is drawn for the northern hemisphere. So this is northern hemisphere summer. Maybe even that title should be up over here. Northern hemisphere summer, northern hemisphere fall, northern hemisphere winter, northern hemisphere spring. And we can see as the Earth is going around the sun, like so, that's going to take a year to do that, to go around the sun. Here we go. In this case, our summer, you can see how the northern hemisphere is kind of pointing towards the sun. The southern hemisphere kind of pointing away from the sun. This, by the way, is summer for the northern hemisphere, but winter for the southern hemisphere. Let's go 1, 2, 3, 4, 5, 6 months later until we get to northern hemisphere winter. Can you see? This would be in December, by the way. So in December 21st, plus or minus a few days, we see the peak of this relationship of how the northern hemisphere, in this case, is pointing away from the sun. We've got the northern hemisphere with very little in the way of light and very long nights, and the southern hemisphere is getting really basked in sunshine. So here the sun is coming in at a very strong angle, the sun is up a long time, and southern hemisphere, first day of their summer, whereas the first day of northern hemisphere, winter. Okay, so as the Earth goes around the sun with that constant axial tilt, the place where the direct ray of the sun will strike the Earth changes or migrates throughout the year. So basically, the direct ray of the sun will hit the equator in March of every year, let's say the 21st plus or minus a few days. So let's say March 21st plus or minus a couple of days. In April, the direct ray of the sun is heading north of the equator. Into May, it's heading about 16 degrees north of the equator. We get to June 21st, and the direct ray of the sun strikes the Earth at about 23.5 degrees north of the equator, the furthest it will get. That will be the first day of summer for the northern hemisphere because the energy of the sun is now focused as far as it will be all year into the northern hemisphere. As we get into July, the direct ray of the sun is now migrating further south, about 16 degrees south. Get into August, about 8 degrees south. Get into September, back at the equator. October, into the southern hemisphere. Into November, about 16 degrees south, and finally about December the 21st, plus or minus a couple of days, the sun's direct ray will migrate as far south as it will get, 23.5 degrees south, and again, that's on December 21st, plus or minus a couple of days. So that vertical ray of the sun, sometimes called the subsolar point, will migrate back and forth, back and forth. So it will go December, January, February, March, April, May, June, July, August, September, October, November, December, January, February, March, April, May, June, etc. The furthest it will get, north of the equator, 23.5 degrees north on June 21st. And the furthest south it will get would be December 21st, 23.5 degrees south. This would be the first day of summer for the southern hemisphere, the first day of winter for the northern hemisphere. Conversely, June 21st would be the first day of summer for the northern hemisphere, the first day of winter for the southern hemisphere. Now, in between, go from June, July, August, September, when the sun's direct ray strikes at the equator, and again in, let's see, October, November, December, January, February, March. So March and September, the direct ray of the sun is striking at the equator. And that means as the Earth spins on its axis, we're seeing, every place on the planet is seeing 12 hours pointing towards the sun, 12 hours pointing away from the sun. So we get 12 hours of light, 12 hours of darkness, equal amounts of day and night. The Latin word for equal is equi, and the Latin word for night is nox. So these are equinox dates. March 21st, plus or minus a couple of days. September 21st, plus or minus a couple of days. Now, it is true that it's not always the 21st, but it will always be within a couple of days of those dates. So I'd rather you remember the months than the specific days. So we have a position here called the, when the sun's rays strike at the equator, we have the March equinox. Then we go to the June solstice, then the September equinox, December solstice, March equinox, June solstice, September equinox, December solstice, etc. I think by now you've got the pattern. So here we see on December 21st, the direct ray of the sun or the subsolar point striking, so the vertical ray striking what we call the subsolar point, 23.5 degrees south of the equator. And then 6 months later, on June 21st, we'd see the direct ray of the sun striking at 23.5 degrees north of the equator. So the subsolar point there, 23.5 degrees north. And can you see in these two examples? In June, so June 21st plus a couple of days, look how the North Pole would be in light all day long, all night long, 24 hours of daytime, 24 hours of daylight. Where on that same date, June 21st, the southern hemisphere, let me get my head out of here. Let's see if I can get my head out of here. Here we go. The South Polar region would not see daylight at all. 6 months later, December, the northern polar region, so the Arctic, doesn't see any daylight at all, whereas the Antarctic would see 24 hours of daylight. So clearly, December 21st is going to have the southern hemisphere having the majority of light, and that coming in at a high angle, and very little in the way of nighttime. That same December would see northern hemisphere very little in the way of light or daytime and long nights. Even when the light came into the northern hemisphere, it would be at a pretty low angle on that date. So again, why do we have seasons? We need two things to be happening here. One, the Earth has to go around the sun. That 365 and a quarter day pattern of one orbit or one revolution is required in order for us to have seasons. And the second thing is this constant axial tilt, so that part of the year the northern hemisphere points towards the sun, and 6 months later the northern hemisphere is pointing away from the sun. So the axial tilt combined with revolution is why we have our seasons. What are the effects of the seasons? Well, the solar rays are more intense in one hemisphere compared to the other from one season to the next. The height of the sun in the sky is different from one season to the next. The days are long for 6 months of the year compared to the other 6 months of the year. And that's, of course, going to give more of an opportunity for the Earth to absorb energy in different portions of the planet and warm up in different portions of the planet. We can see from this graph here that based on latitude, let's say here 70 degrees north of the equator, so let's say northern Sweden, maybe even Alaska, 24 hours of daylight in June, July. But those same places would have no daylight as you get into December and January. Let's say a place at the equator, January, 12 hours of daylight. June, 12 hours of daylight. December, 12 hours of daylight. So you can see from this diagram that the higher your latitude, the further you are away from the equator, the greater the difference will be between your wintertime and summertime daylight hours. For LA, we're very close to 30 degrees north latitude. We're about 34 degrees north latitude. We would see for LA just about 10 hours of daylight hours in January and December. And let's get to June, July, we'd be looking at about 14 hours over here, 14 hours of daylight hours in June, July. Okay, so I think we can see from here, we do know why we have seasons, what causes them. We can identify perihelion and aphelion based on the distance between the Earth and the Sun. We know that those do not cause the seasons. We can identify the solstices of June 21st and December 21st, and where the subsolar point or the direct ray of the sun will strike. Again, that would be 23.5 degrees north of the equator and 23.5 degrees south of the equator. In our equinoxes, we can clearly identify those as occurring on March 21st, plus or minus a couple of days, September 21st, plus or minus a couple of days. And the Earth-Sun relationships are pretty much the same on those two dates. Now, daylight hour changes. This says from March 22nd, which is the day after the March equinox, all the way till September 20th, which is a day before the September equinox. And the middle portion here, the middle of that time period would be June 21st. During that half of the year, the rays of the sun are in the northern hemisphere, or they are favored in the northern hemisphere. The subsolar point is located in the northern hemisphere. A day after this, that's September 21st, plus or minus a couple of days, the sun will be at the equator. The direct ray of the sun will strike the equator. From September 22nd all the way through till March 20th, and the center of that time period would be December 21st, the direct ray of the sun will strike in the southern hemisphere. So the subsolar point will be located in the southern hemisphere. So there will be longer days and shorter nights for the southern hemisphere between those two dates. For the northern hemisphere, we would see longer days and shorter nights between these dates, that other half of the year. Okay, we're getting towards the end of this chapter now. I know this has been brief, but it should be a good reminder for you. How do we locate ourselves on this oblate spheroid? If we had no addresses, no physical features, we'd still have to locate ourselves, and we can locate places on other planets this way, or anything that's almost a sphere, anything that is even a slightly more oblate spheroid than our own. We have to do this through a system of latitude and longitude lines intersecting each other. So these are lines of latitude. See these ones that are running kind of east-west? This is a line of latitude. This is a line of latitude. And the most famous line of latitude is this one right here. That's the equator. That's a line that's running east and west. But, as we'll see in a second, these lines are telling us how far away from the center of our planet we are. How far north from this line? How far north from this line, or how far south from this line? The opposite running lines are lines of longitude, and those always start at the pole and go all the way to the other pole. So they are running north-south. North-south running lines. Those are called lines of longitude. So where those intersect, we can locate ourselves. So in this diagram, if we said like this point right there, that point right there is 10, 20, 30, 40 degrees north of this equatorial line. So it would have a latitude of 40 degrees north right there. That same point, we can say how far is it from a starting point, any line running north-south, but that would be a starting point for east-west measurement. So we can measure from here how far any place is from that line in terms of its longitude, how far this way or how far this way. In this case, this place right here is located 10, 20, 30 degrees west of that line. So we have a longitude right there of 40 degrees north and 30 degrees west. Well, let's get a little bit more specific than that. So these are lines of longitude shown in this diagram. Lines of longitude run east-west, but each of these lines are telling you how far they are from our starting point, which is called the equator. So the equator has a longitude of 0 degrees because it's not north or south of the equator, it's at the equator. So here we have a 0-degree line. This is the equator. So these lines, as you can tell mathematically, they are all parallel to one another. So we call lines of latitude parallels. So lines of latitude run east-west, but they measure how far north or how far to the south the place is from the starting point. So the definition would be the angular measurement, so this is for latitude, the angular measurement of how far a place is located to the north or to the south of a starting point called the equator. Latitude and longitude are both measured in degrees, minutes, and seconds. If you need a refresher on that, check out the Khan Academy. Again, the Khan, K-H-A-N Academy, and just look up degrees, minutes, and seconds, or look up degrees of latitude, and it will give you a little tutorial. So these parallels, they run east-west, they measure north and south. The key lines are the equator, located at 0 degrees, the Tropic of Cancer, located 23.5 degrees north latitude, the Arctic Circle, 66.5 degrees north latitude, and the North Pole, 90 degrees north latitude. That's our furthest or our largest measurement for latitude. You can't get any more than 90 degrees away from the equator. Southern Hemisphere, Tropic of Capricorn, located 23.5 degrees south. The Antarctic Circle, Antarctic Circle is 66.5 degrees south, and the South Pole is located at 90 degrees south. So those are the key lines of latitude. Now, only one of these cuts the Earth into 2 equal halves, and that is the equator. Every other one would cut the Earth, but not into 2 equal halves. Like, let's say if we cut it here, we'd have a big half below and a very small portion above. So the equator is the only one where it's 25,000 miles to go all the way around. And that 25,000 miles to go all the way around would also equate to 360 degrees to go all the way around. So every degree that you move along the equator, if you move along the equator, you're not moving north, you're not moving south, you're moving either east or west. In this case, right here, I'd be moving to the east. So every degree I moved would be along a great circle. So every degree would be 69 miles, 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 69 miles. If I did that all the way around the Earth at the equator, I would go 360 degrees. Each degree was 69 miles. I'd come back to my starting point, and I would have gone about 25,000 miles. Now imagine going around the Earth east to west, not at the equator. So if we did it at the Tropic of Cancer, if I went around the Earth here, it wouldn't be 25,000 miles to go all the way around. It'd be much less than that, maybe 15,000 miles. Way up here in the Arctic Circle, if I went around the Earth, that wouldn't be 25,000 miles. That might be 6,000 miles. So instead of being 69 miles for every degree, maybe we're looking at about 15 miles per degree. And this reaches its ultimate low spot right here at the North Pole. So at the North Pole, you can just spin around and you don't go anywhere. But you can walk around this designated spot, just walk around it and say, I just went around the Earth. I just went 360 degrees around here, but I didn't go anywhere. I might have moved a few feet. So that's pretty much 0 miles per degree of east-west motion. You want to win a bet, go around the Earth, get yourself up to the North Pole, do a quick circle. You'll probably be faster than anybody else. Okay, so the other half of the geographic grid, that of longitude. Now, it must sound silly, but basically all lines of longitude are the same long. That makes sense? Longitude lines are long, latitude lines are flat. So lat is flat and long is long. So lines of longitude. These are lines that start at the North Pole and go all the way to the South Pole. So they're all about 12,500 miles in length. Each of those are called meridians. So here's a meridian, here's a meridian. And we basically have these lines. They are imaginary lines. We have them starting at the prime meridian, the 0-degree meridian, the one that runs through Greenwich, London, England. That's our starting point by convention. We agreed to it in the 1880s, and since then, pretty much every country has agreed that's where we start as that is our starting point for how far away from that line we are in terms of our longitude. So lines of longitude are measuring how far a place is to the east or to the west of the prime meridian. Again, from the North Pole to the South Pole. Now, the prime meridian itself is at 0 degrees. You can go a half of a planet to the other side over here before you start coming back upon yourself. So the maximum measurement for longitude is not 90 degrees, but instead it's 180 degrees. And that line is associated with something we call the international date line. Now, by the way, if you're traveling along a meridian, you're always traveling north or south. And therefore, you're always traveling upon a great circle. It would take you 25,000 miles to come all the way around. So if you go from the North Pole to 89 degrees south, you just went 69 miles. If you went from the North Pole to 89 degrees north, you just went 69 miles. If you go from 89 degrees north to 88 degrees north, you just went another 69 miles, etc. So if you're traveling north or south, you're always going to be traveling 69 miles per degree change. Okay. Time zones. Time zones are artificial allocated time based on a system where we try to get everybody to get their noontime sun very close to a clock that would read noon, or maybe getting sunrise somewhat close to 6 a.m. and sunset somewhat close to 6 p.m. on average. Well, because the Earth is spinning around or rotating once every 24 hours, the only way to do this would be to assign different time zones every 15 degrees of longitude apart. So basically, the Earth spins 360 degrees in 24 hours. That means in 1 hour, we would only spin from the west towards the east, the way we always spin. We would spin or rotate 15 degrees. So the centers of time zones start at the prime meridian, and that time zone, by the way, will go halfway to the next. It goes 7.5 degrees to the west and 7.5 degrees to the east of that. So the prime meridian would be the center of a time zone. The center of the next time zone would be 15 degrees to the west. Next one after that, 30 degrees, and then 45 degrees, and then 60 degrees. So every 15 degrees, we've got the center of a new time zone. And in essence, what that means is if you are in London, all the time zones to the west, they haven't spun yet, they haven't rotated to the position of London. And because the Earth is going to rotate from the west towards the east, the clocks back here have to be 1 hour behind, 2 hours behind, 3 hours behind, 4 hours behind, 5 hours behind, 6 hours behind. So New York would be about 5 hours behind the time of London. Los Angeles is almost 120 degrees to the west of London, and that's 8 different time zones. So Los Angeles is 8 hours behind the time of London. So in essence, as you go to the west, you can take your watch and make yourself an hour younger, an hour younger, an hour younger, and so forth. So you can get younger, 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 younger. But that, let's see, we'll stop over here. That operates in the opposite direction if you go to the east. You get an hour older, 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 etc. So you go into the east, you're getting older and older and older and older. Well, at some point, going east brings you out to the west. So these have to reconcile at some point. So for every hour you've been getting younger as you've been traveling to the west, if you cross the 180-degree meridian, or the international date line, you all of a sudden will lose a whole day. Boom, by crossing that line. So that's what the international date line is. It's a reckoning point for all those hours that are being lost going to the east, or the hours that you basically you gain extra hours by going to the west. But if you cross the international date line, traveling from west to east, you lose that day. If you travel from east to the west, you get a whole day back, a whole 24 hours. So it is possible to be east of the international date line, cross by heading further east. Now you're in the western hemisphere. So once you cross that date line, you would get a whole day back. You could leave on a Saturday night and arrive somewhere hours later on a Saturday morning, the same Saturday morning. You could arrive before you left. I know it sounds crazy, but it can happen, and it does happen all the time. So, all right, we're at 42 minutes. I think that's long enough for this. I will post the video, that 3-minute video that I talked about, and I wish you all luck. I hope this was a helpful, quick review, and we'll see you soon. Bye-bye.